All right, today we will solve systems where the eigenvalues are complex, just like for second order ODE. And in particular, let's solve x prime equals ax and draw the phase portrait where A is the matrix -2, 4, -2, 2. And as usual, the first step is to find the eigenvalues. And here, let's do it because it's different. So let's calculate Muhammad Ali. So determinant of A minus lambda I. So -2 minus lambda, 4, -2, 2 minus lambda. And again, be super careful of your algebra here because the eigenvalues determine everything. So -2 minus lambda times 2 minus lambda -4 times -2. And this becomes, I think, -4 plus 2 lambda -2 lambda plus lambda squared. Again, plus 8. Nice thing is this cancels out. And you get lambda squared plus 4, which you set equal to 0. And essentially, lambda becomes plus minus I. So plus minus 2i. Now the trick is here, turns out you only need one eigenvalue. So pick whichever one you like. Let's say 2i. I'll explain later why. So step 2, let's do lambda equals 2i. Again, you can pick lambda equals -2i. Either choice is fine. And let's do null space of A minus lambda I. So A minus 2i, I captain. And which becomes, let's see, in this case, so I think -2 minus 2i. And then 4. And then -2, 2 minus 2i. And then 0, 0, again, because we're doing null space. And let's clean this up a little bit. So we can, for instance, divide this by -2 and divide this by -2. And you end up getting, I believe, 1 plus I. And then -2, 0. And then 1 plus I, 0. Here's a little trick that I allow you to do for complex eigenvalues. But since the eigenvalue is 2i, from linear algebra, one of the rows has to be all zeros, which we've seen for the distinct eigenvalue case. So just pick any row you want and make the other row 0. So trick. And it does not matter which one you pick. So trick, pick your favorite row. And make the other 0. And the other 0. 0, 0, 0. For example, let's pick the first row. Again, completely arbitrary decision. And let's make the other one 0. So let's do 1 plus I, -2, 0, and everything else. Let me repeat. Because 2i is an eigenvalue, from linear algebra theory, one of the rows is eventually 0. Pick any you want and make the other one 0. And now this tells you that 1 plus I x minus 2y equals 0. Here, again, in my opinion, it's easier to do the guessing game. So in this case, x equals 2 and y equals 1 plus I works. And you can check, because 1 plus I times 2 minus 2 times 1 plus I equals 0. And so an eigenvector for lambda equals 2I gives you 2 and then 1 plus I. And I do want to say, and I will say this again, there are multiple correct answers here, depending on which eigenvalue you pick, and which row you pick, and which guess you pick. Now, here's the good news. We did it for 2I. The good news is we don't need lambda equals minus 2I. Good news. Don't need lambda equals minus 2I, because just like for complex roots, one complex eigenvalue is as powerful as two real eigenvalues. And we have seen this before in second order ODEs, where we didn't use, let's say, r equals 2 minus 3i. We just needed r equals 2 plus 3i. But in case you are curious, had you done this for lambda equals minus 2i, you would have gotten the complex conjugate, which is 2 and 1 minus I. So it is true in linear algebra that the eigenvector of the complex conjugate is the complex conjugate of 2 and 1 plus I. But again, completely useless information. Okay, and now the question is, how do you build your solution? So step 3, solution. Once again, for lambda equals 2i, we found 2 and 1 plus I. And remember, what this tells us is we can build our solution. E to the eigenvalue t times eigenvector. So it tells us that the following is a solution. Namely, once again, e to the eigenvalue t times eigenvector. So e to the 2it times 2 and then 1 plus I. And just as before, for complex roots, all we want to do is split this into real and imaginary parts. So split into real and imaginary parts. So remember, this becomes E, and we want to use Euler's formula, so E of 2ti, and then 2 plus 0i, and then 1 plus 1i. Okay. And then this now becomes, remember by our friend Euler, cosine 2t plus I sine of 2t, and then times, I think, 2, 1 plus I 0, 1. Pull this out. So I just want to tell you, we're having a full party right now, and you're all invited to it. So this becomes cosine 2t times 2, 1 plus I cosine of 2t times 0, 1 plus I sine of 2t times 2, 1 and then plus I squared, which is really minus 1. So again, this thing is I times sine of 2. Times sine of 2t times 0, 1. And then once again, as I said, we want to split this into real and imaginary parts. So this becomes cosine of 2t times 2, 1 minus sine of 2t times 0, 1. Again, the minus comes from I squared, and then plus I times what are called the cross terms. Well, I times cosine 2t, and then 0, 1 plus sine of 2t, 2. Why does this matter? Well, just like for second order ODE, one complex solution is as powerful as 2 real solutions. And in fact, it turns out, and this is true, both the real and imaginary parts of this solve the ODE. So fact, both the real and imaginary parts solve x prime equals ax. So in particular, this tells you that both cosine 2t, 2, 1, minus sine 2t, 0, 1, and the cross terms, cosine 2t, 0, 1, plus sine 2t, 2, 1, solve this. The ODE. And essentially what this is, those two things are bases of solutions, and all you have to do is take linear combos. And this is really by analogy. Okay? Because let's say if we had y double prime plus y equals 0, this is the analog of finding simply cosine of t and sine of t. From which we built a cosine t plus b sine t. Okay. And it turns out the solution is simply C1 times the first vector plus C2 times the second vector. So once again, to recap, we found the basis of solutions and we just take linear combinations. So maybe let's do step 4. Solution x of t is C1 cosine 2t times 2, 1 minus sine of 2t, and then 0, 1. That was that first part in blue, plus C2 cosine 2t. So the cross terms, 0, 1 plus sine of 2t times 2. So the first thing is almost like a dot product. The second term is like the cross terms. And completely optional, you can rewrite this as one vector. So C1 2 cosine of 2t again plus 0, and then cosine 2t minus sine of 2t, and then plus c2. 2 sine of 2t, I believe, and then cosine 2t plus sine of 2t. Ta-da! I know this looks a little bit like a nightmare, but it looks long because I explain things. No, I explain things thoroughly, but you'll see in practice, especially with the next example, that it's much quicker in practice. Unfortunately, we're not quite done. We still need to draw the face portrait. Step 5. Face portrait. Now, because of the cosine and sine, there is something circular going on, because you see cosine sine like spins me right round. Okay. So the solutions, you might think they're circles, but not quite, because of those constants C1 and C2, the solutions are actually stretched out circles, which are ellipses. So here, the solutions, so because of cosine 2t and sine of 2t, solutions are ellipses. So really, to draw this, draw the ellipses and just draw them slanted, because it turns out here the axis is more diagonal. Maybe like this. Oh, very nice. Just like that. And I do want to tell you from the outset, you do not need to know how to find the axes of the ellipses. Those are very hard to find, and I kind of outlined this in the notes how to find them, but they're not just the eigenvectors. It's a little bit harder. That said, you are responsible for finding the orientation, whether it goes clockwise or counterclockwise. And it turns out it's easy to, or straightforward to find them, because the way you do it is pick any vector you want, say 1, 0. So for the orientation, here orientation. So whether it goes clockwise or counterclockwise, pick any vector, at least any non-zero vector. Say 1, 0. Again, literally any vector that you want. You know, I just picked 1, 0 for convenience. And consider that as your initial condition. And the nice thing is, the ODE tells you which direction the vector goes, or the solution. So once again, this is 1, 0. Then by the ODE, the ODE literally tells you the derivative of your solution, let's say at 0, is a times your solution at 0. So x prime equals ax. So x prime initially is a times x initially. And that becomes -2, 4, 2 times 1, 0. And that becomes minus 2 times 1 plus 4 times 0 minus 2 times 1 plus 2 times 0, and that becomes minus 2 minus 2. So let me recap. Pick any vector, let's say 1, 0, choose that as your initial condition. The ODE tells you x prime initially is a times x initially. So at 1, 0, the solution goes in the direction minus 2 minus 2, which I believe, so you go 2 to the left and 2 down. So it goes in this direction. Do it in green. It goes in the direction minus 2 minus 2. So this tells you that actually the solutions, they have to go clockwise. So they have to go in this direction, because otherwise it wouldn't check out with the arrows. Again, one's here and one's here. And the cool thing is, this gives you an easy way to check for the orientation. Minus 2 minus 2. And once again, you are not responsible for knowing the axes here, but you are responsible for finding the orientation of this. In the next example, we'll see all this is much faster in practice.